So hi everybody. Today's lab is on sound, and let me just recap very quickly some of the concepts that we covered in lecture that deal with sound. So sound is basically a longitudinal wave that can move through some kind of material. If we're thinking about air as the medium that carries a sound wave, which is usually the case, then we can think of a sound wave in terms of air molecules vibrating back and forth around some sort of equilibrium position. We can also think of a sound wave in terms of pressure variations. Okay, so at some locations within a sound wave, the pressure will be higher because the air is compressed. Other locations, the air will be lower pressure than normal because it's expanded a little bit. So this repeated expansion and compression of the air is one way we can think of a sound wave moving through the air. That brings us to microphones, which are basically designed to detect those pressure variations in the air when there's a sound wave present. So inside of this microphone, and this is basically how every microphone works, we have a small membrane called a diaphragm. Okay, so when the sound wave comes in and hits the diaphragm, it makes the diaphragm vibrate back and forth with the same exact frequency that the sound wave has. So basically, we're able to capture what's going on with the sound wave by making the diaphragm vibrate back and forth. That can be converted to an electrical signal. Those vibrations in the diaphragm can be converted to an electrical signal, and we can send that to the computer so we can actually visualize the data, make graphs of the actual waveform of the sound wave that we're recording. So this is our source of sound that we're going to be using in today's lab, a tuning fork. So we actually have a whole set of tuning forks, but each one is designed to ring with a very specific frequency. Okay? That's why they're useful for tuning instruments. So this one right here is designed to resonate at 512 hertz. So let's take the tuning fork, strike it on something, and you can hear the sound it makes. Okay? So basically in this lab we're using this microphone to record the sound waves created by tuning forks, and we'll investigate different properties of sound that way. Okay, so the first thing we're going to do is measure the waveform of the sound wave created by this tuning fork, which is designed to ring at 128 hertz. So here's what I'll do. I'm going to basically bang this tuning fork on the desk, put it right next to the microphone, and now I'm going to start collecting data. So this is a graph of our data. On the vertical axis here, you have pressure. So this is air pressure on the vertical axis, and on the horizontal axis here you have time. So what this is showing us is that the air pressure is varying with time in a way that kind of looks like a sine function. It's just going up and down, i.e. as the sound wave hits the diaphragm of the microphone, the air pressure oscillates up and down in this sort of periodic way. So that's what we'd expect from a sound wave. Now, one thing you might notice about this is it's not a perfect sine wave. Okay, so there's these sort of jagged edges inside of our wave. What's the reason for that? Well, part of the reason for that is when you hit a tuning fork, it doesn't actually just vibrate with one frequency. There's a mix of different frequencies in there, and this is just what it looks like when you have a sound wave with a mix of different frequencies. But there's obviously one dominant frequency here. Okay, just look at the overall larger sine wave, and what we can do is measure the frequency of that. So the way we can do this is by noticing how much time passes as you go from one peak of the wave to the next. So one way we can do this is simply, measuring the time to go from, let's say, this peak to the one to the right of it, but we can get a much more accurate sense if we average over several periods. So here's what we're going to do. If I start on this peak right here, and then drag one peak to the right, that's one period. Okay, that's 2 periods, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 periods right there. So what we can do is measure the time for this sound wave to undergo 10 periods. The time is read out right at the bottom of the graph, so I'll just tell you what this is in case you can't see it. The time to undergo 10 periods is 0.07769 seconds. Again, that's 0.07769 seconds. Okay, so the next one is a 256 hertz tuning fork. And just like before, we're going to hit it on the desk, put it up to the microphone, then collect the data. So here we go. And here's what the data looks like. So you'll notice that this is a higher frequency sound wave than what we had before for the 128 hertz tuning fork. And the way that looks when we plot this out is the sound wave is oscillating faster. So the peaks are closer together in time than before. That's exactly what we'd expect. So same thing, we're going to take our cursor, we're going to put it here at this peak, and then we're just going to drag it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're capturing 10 peaks here of our sound wave. So that's 10 periods of oscillation. The time it takes is 0.03988 seconds. Okay, so the next part of this lab involves beats. So if you remember from the lecture, beats are what happens when you play two sound waves that have two slightly different frequencies at the same time. So when you look at the overall combined sound wave, when you have these two slightly different frequencies there, what you get is a periodic rising and falling of the sound intensity. That's what the beats are. So it's probably easier just to show you than try to explain it. I have two different sources of sound here that have two slightly different frequencies. I'm going to show you what happens when I play them at the same time. So real quick, this is a 512 hertz tuning fork. I haven't really done anything to it. This is an identical tuning fork, so it's designed to ring out at 512 hertz, but I've altered it by putting a piece of tape at the top of the two prongs. So by adding the tape, I've increased the mass of these prongs. Because I've increased the mass very slightly, they're going to move a little bit slower than they normally would, and they're vibrating slower. That means the frequency is a little bit lower than it normally would be. So I have something that's at 512 hertz and something that's a little bit less than that playing at the same time. Here's what it sounds like. Okay. So you'll notice that there is certainly some kind of tone there, but what's happening is that tone is rising and falling in intensity. Those were the beats that you heard when we played these two tuning forks together. Okay, so the next thing we're going to do is actually record the waveform of the sound that's made when we play these two tuning forks at the same time. So let's start by hitting them both. Okay, so this is the data, and if you take a look, you'll notice that the waveform looks a lot different than before. So what you see here is, on the time axis, we're going from 0 to 2 seconds. So this is a lot of time we're covering here. I'm going to show you what it looks like when I zoom in much closer. But when we're zoomed way out and we're seeing 2 whole seconds pass, what we notice are very, very long oscillations. Now these are the beats that I was talking about earlier, these risings, this rising and falling of the sound intensity. You can see that happening right here on the graph. So what we want to do is calculate the beat frequency. The way we're going to do that, just like before, is I'm going to go to one peak, okay, and then I can just drag over and see how much time passes until I get to the next peak. That would be a period. But instead of just doing one period, like before, we're going to average over 10. So that's one beat, 2 beats, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's 10 beats. The time it takes to undergo 10 beats is 1.328 seconds. So the time for 10 beats is 1.328 seconds. Okay, so I'm going to show you what it looks like when I zoom way in on the waveform. Right now, you're seeing 2 whole seconds of time pass. Let's see what happens if we zoom in to, let's say, 1/10 of a second. Okay, so now, oops, that's not what I wanted to do. 1/10 of a second. There we go. So in this window, 1/10 of a second is passing, and you can now see those much smaller oscillations that I was talking about earlier. So instead of the beat frequency, what we're seeing here is the frequency of the tone that we're hearing. Okay? So what I'm going to do is measure this frequency by starting at one peak and then covering 10 whole cycles of oscillation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the time that we have, the time that elapses, is 0.01991 seconds. So 0.01991 seconds. All right, so the next thing we're going to do is measure the individual frequencies of these two tuning forks just by themselves. So let's start with the one with no tape on it. And then we can measure the frequency by looking at this graph. So just like before, we're going to capture 10 cycles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cycles right there. And the time for these 10 cycles is 0.01972 seconds. So 0.01972 seconds. Okay, and then we'll look at the tuning fork that I put the tape on. Again, I want to know the frequency of this one just by itself. So here we go. So the way that we'll get the frequency of this one is, again, to start at one peak and then just drag and then capture 10 periods. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 periods right there. And so the time for 10 periods is 0.02001 seconds. So we have 0.02001 seconds. So the last part of the lab that we're going to do today is a measurement of the speed of sound as it travels through the air. So here's how this is going to work. I have a microphone right here, and then I have a tube that's open at this end, but closed at this end in the back. This is all we're doing in the experiment. We're simply going to snap our fingers like this, okay, at the opened end of the tube, and the microphone is immediately going to pick up that sound wave, okay, because there's almost no distance between my fingers and the microphone. But there's also a sound wave that goes into the tube, it reflects off the back wall, and then back out into the microphone. So basically, the microphone is picking up that original sound wave plus that echo or that reflected sound wave that goes through the tube. Now, the original sound wave has almost no distance to travel to get to the microphone. The reflected sound wave has to travel about 2 meters because, again, it has to make the round trip there and back to get to the microphone. So there's going to be a delay between the original sound wave and the reflected wave. If we can measure that time delay, we can then use that to measure the speed of sound. That's the idea behind this experiment. So the first piece of data that we're going to need is exactly how long is this tube from where the microphone is placed to the back wall. So if we use our meter stick to measure that, here's what we get. So I'm getting 102.5 centimeters. So the length that you should use is 102.5 centimeters. So now let's record the data. And this is what it looks like when we plot it out. So the snap of the fingers looks like a pulse when we view its waveform. And what we see here is the first time you see that pulse, that's the original sound wave. The next time you see that pulse, that's when the reflected wave comes back into the microphone. So what we want to know is, what is the time delay between those two pulses? And we can just measure that straight off the graph. So here, I'm going to start at the beginning of the first pulse, go to the next one. That's when the reflected wave goes back into the microphone. And the time we get is 0.0063 seconds. So 0.0063 seconds. So for that last experiment, I actually did 4 more trials. So there were a total of 5 trials for that speed of sound experiment. I'm not going to show you all those on the video. I'm just going to give you the data on the screen at the end of this video for the other 4 trials. And that will actually do it for today. In this lab, we explored many different aspects of sound that we've been talking about in lecture, and so I hope you do get some appreciation for that. So I'll see you in the next one. Until then, I hope you're doing well. Be safe out there.